Hello, in this video I'm going to be going through this problem here on radioactivity, so I'll first read it out to you. A certain preparation includes two beta-active components with different half-lives. The measurements resulted in the following dependence of the natural log of preparation activity on time t expressed in hours. And here you can see the data that they have measured, so the log of the activity of the sample against time t, which is expressed in hours. And the question is asking us to find the half-lives of both components and the ratio of radioactive nuclei of these components at the moment t equals 0. Okay, so the first thing you can do to solve this question is first actually plot this data that they've given here. So I've already done that here. So here is a graph of the log of the activity against time, and as you can see, it's a pretty exponential graph, but obviously the question's made more complicated because there are two components here instead of one radioactive component. So if there was just one radioactive component, we know that the general expression for the activity of a sample, so activity A, activity is equal to lambda n e to the power minus lambda t, where lambda is the decay constant of that particular radioactive element and n is the initial number of nuclei in that sample. So that's a general expression for activity. But in this question we have two radioactive components, and so we're going to have to modify this expression for activity. So if we say that the decay constant for the first component is lambda 1 and so on, so A is equal to lambda 1 n1 e to the power minus lambda 1 t plus the activity of the second component. So the overall activity is a kind of superposition of the activities of the two separate components. So plus lambda 2 n2 e to the power minus lambda 2t. And right now we don't know any of the values of lambda 1 or n1 or lambda 2 or n2, but over the course of this problem we can make some assumptions and use some trial and error to find out these values. Okay, so the first thing we can assume, so the question told us that these two beta-active components have different half-lives. So I am going to assume that the half-life of component 1, so if I call that TH1, I'm going to say that is smaller than the half-life of the second component, TH2. And therefore the first component is going to be decaying much faster than the second component, and so when the time t is much greater than the half-life of the first component, we would expect the activity of the first component to be very low, and the activity would be roughly equal to just the activity of the second component. So when t is much greater than TH1, we would expect the activity to be approximately equal to just the activity of the second component. So I'm going to call that A2. So we can essentially just ignore this part of the equation and just write the activity is equal to lambda 2 n2 e to the power minus lambda 2t. And the reason I'm making this assumption is because from the graph we can actually see that when t is large, so say from like 10 to 20 hours, the graph is actually pretty linear, like that's practically a straight line. And that matches with the assumption we have made, because if we take the log of this equation, we get ln a is equal to ln lambda 2 n2 minus lambda 2t. And we can see from this equation that it is linear, so it's got a constant part and t, which is multiplied to a coefficient of t, and so we can see that the gradient of this graph would be equal to minus lambda 2, which matches here, so we can see there's a negative gradient here, so that means this gradient here is equal to the value of lambda 2. And so I can work out the gradient of this line. So if I just do it for in between if I do it for in between 14 and 20 hours, so between these 2 points here, I can say that delta ln a over delta t, that is equal to 1.32 minus 0.9 over 6. And that is equal to around 0.07. So that's a gradient of this line, which we have shown is equal to the value of lambda 2. So lambda 2 is equal to the gradient that we've just worked out, 0.07. So now if we consider the first part of the graph, and we notice that this section is also linear, it's a straight line, so from around 0 hours to 3 hours, that is clearly a straight line. So again, this tells us that when t is small, the activity of the sample, it was dominated by one of the components, and we have said that TH1, the half-life of the first component, is smaller than the half-life of the second component. So we can say that when t is small, the first component is going to be decaying much faster than the second component. So when t is small, in this section of the graph, the activity is dominated by the first component. So if we do something similar and we work out the gradient of this line here, so here lambda ln a, delta lambda ln a over delta t, and if I do it between 0 and 1 hours. So that's equal to 4.1 minus 3.6 over 1, so just 0.5. Now, we know that when t is small, we know that the activity is dominated by the first component because it has a shorter half-life and so it's decaying faster. But at this time, the second component, it is also decaying, just at a slower rate. So we have to take that into account, and unlike as we did over here to work out lambda 2, we can't just simply ignore the activity of the second component. We have to take it into account. So if we say that this gradient here is a kind of superposition between the activities of component 1 and component 2, and we're just trying to work out lambda 1, then we can say that lambda 1 is equal to the gradient of this line, so 0.5, minus the value of lambda 2 that we worked out before, 0.07. So we can say that lambda 1 is equal to 0.5, so this gradient here minus this gradient here, 0.07. Which equals 0.43. So those are the two decay constants of the two components. And now that we have the decay constants, we can calculate the half-lives, because we know the relationship between the half-life and the decay constant of any radioactive element. So T half, just generally T half is equal to ln2, so the natural log of 2 over the decay constant. So using this equation, we know that TH1, the half-life of component 1, that comes out to be 1.6 hours, and TH2 is 9.8 hours. Okay, so that's the first part of the question done, which asked us for the half-lives of both components. And now, so the second part of the question asked us to find the ratio of radioactive nuclei of these components at the moment T equals 0. So if we look at our main equation here of the activity of this preparation, we can see that when T is equal to 0, so this becomes e to the power 0, and that becomes e to the power 0, which is just 1. So when T equals 0, we can see that the activity A is just equal to lambda 1 n1 plus lambda 2 n2. And the question is asking us to find the ratio of the radioactive nuclei. So we are looking for n1 over n2. so that ratio. So we also know from the data given in the table, we know that when t equals 0, the value of ln A was 4.1. So we know that ln A is equal to 4.1, and so we can work out the value of A, the activity, when t equals 0. So A is equal to e to the power 4.1, which is 60.34. And so if we substitute this value of A and the values of lambda 1 and lambda 2, which we've calculated, which you've just calculated over here, we substitute those values into this equation, we get 60.34 equals, so lambda 1 was 0.43, plus lambda 2, which is 0.07. And because we are trying to work out n1 over n2, if we divide everything by n2, then we get 60.34 over n2 equals 0.43 n1 over n2 plus 0.07. So we just want this n1 over n2 part, but so that we can see we need the value of n2. Now remember, we have this equation here, so when t was much greater than the half-life of component 1, we saw that the activity was approximately equal to just the activity of component 2. And then we found out ln A, and we know that this equation is only valid when t is much greater than th1, and so the equation is going to be most valid or most accurate when we choose the maximum value of t that we have. So the maximum value of t that we have is 20 hours, when the value of ln A was 0.9. So if we use these values and put them into this equation in order to work out n2, that should give us the most accurate value of n2. So if we put them in, then we get as the value of ln A at 20 hours was 0.9, so 0.9 equals ln, so the value of lambda 2, 0.07, 0.07 n2 minus lambda 2 t, so 0.07 times 20, so 1.4. And so if we solve this to get the value of n2, we get n2 is equal to 142.5. And so now we can use this value of n2 and put it into this equation, so we can find the value of n1 over n2, which is what the question was asking for. So if we do that, we get n1 over n2, it comes out to be 0.82. So yeah, that was what the question was asking for. Now, when we were doing this question, we've made a lot of assumptions throughout. So, for example, here, when we decided to just ignore the activity of component 1, and in order to see how valid these assumptions are, we can use our formula of the activity A, and we can create our own formula by substituting in the values of lambda 1, n1, lambda 2 and n2. So if I first just work out n1, so I can just work out n1 from here because I know what the value of n2 is now. So n1 is actually 116.85. That's the value of n1. So if I substitute all the values in, so lambda 1, lambda 2, n1 and n2 into this equation, then A equals 50.2455 e to the power minus 0.43 t plus 9.975 e to the power minus 0.07 t. And if I plot this graph using some plotting software, which I have done here, so that's this graph here, and so here this axis is the time axis, so that's time, which was in hours, and this axis is the axis for LNA. Yeah, and we can see how accurate our equation is by comparing it to the graph of the data which was given in the question. So this graph here, so we can compare it, and we've got the values here. So we can see that when t equals 0, our graph is showing that it's around 4, or just above 4, and we can see that the data gave that when t equals 0, LNA was 4.1, so that's pretty accurate. And then when t equals 20, LNA was 0.9, and here we can see that when t equals 20, LNA is just under 1, so that's pretty accurate. And then again, when t equals 10, this graph is showing it's around just under 2, and here it's showing 1.6, so maybe that's a little off, I think. And again, when t equals 5, here that's showing around 2.5, whereas it should be around 2.06, so that's very clearly off. So I think the graph shows that the higher values of t, so between 10 and 20, that's more accurate than the values of t when t is small, and that's probably due to the fact that we made a massive assumption when calculating the value of lambda 1. But overall it is pretty close. But if you do this question and you work out your own values and you form your own equation for A, you can see how close you get to the actual data. Yeah, so you can just put that in the comments if you like, and we can see how accurate you get.